I want to welcome you all to our second lecture on our lecture series on seismic resistant design of multi-story RCC office building based on the Nepal National Building Code 105/2020. In our previous lecture, we discussed on some codal provisions introduced in the updated version of the NBC code, and we compared those codal provisions with the relevant provisions in IS 1893 Part 1 2016. And today we will begin with modeling and analysis of our building in ETABS. Before starting with modeling, let's first look at the AutoCAD plan. So this is our building that we are going to design in ETABS. You can see here we have 1, 2, 3, 4, 5, 6, 7, 8 stories. And among these 8 stories, we have one basement, one ground floor, and remaining 6 stories. Let's see here. This is our basement plan, and the vehicle entry is from this side here. You can see here written vehicle entry, and all of the space in the basement is separated for parking of bikes and car. And we have a lift shaft here, so we have a lift in our building, and the staircase also starts from the basement itself. There are A, B, C, D, 4 grid lines parallel to y-axis, and 1, 2, 3, 4, 5 grid lines parallel to the x-axis. And if you see here, it is not a perfectly rectangular building, but somewhat L-shaped or unsymmetrical building. So this is our basement plan. And remaining, we have the floor plans of the remaining 7 stories. If you look at the ground floor plan, you can see here that this ground floor plan is totally a dining room. You can see tables and chairs arranged here. There is a lift shaft here. The main entry door is through this western side. On the western side, we have a main entry door here labeled as EMD. Our staircase is here, and on this southern side we have a kitchen room, and then we have some storeroom, ladies and gents toilet here, and the remaining whole space is used as dining room. And from first floor plan to, if you see here, 5th floor plan, these are the architectural plans with the same concept or same use here. As you can see, the floor plans are the same for 1st story to 5th story. What is shown here in our AutoCAD plan is that this is an exam hall. We have an exam hall here. So students or some candidates sit here on these tables and give exam in these exam halls. We have a control room here, and we have a waiting hall here on this northeastern side. And from 1st floor to 5th floor, we have storeroom and toilets on the eastern side here. So this architectural plan is the same for 2nd floor, 3rd floor, 4th floor, 5th floor. And finally, on the topmost floor or the 6th floor, we have a staircase cover here. We have lift shaft here, and we have another hall here. You can see here, this is a big hall. Their tables and chairs are not shown in this hall, but we have a big hall here, and the remaining portion is balcony. So this is architectural plan. And if you look at the section of this building, we can see that our basement height is 3.6 meter, and also the floor height for the remaining floors are also 3.6 meter. So we have their elevations of 4 sides, and then we have the section of our building. So let's look at this plan once again. First, we have 4 grid lines parallel to y-axis, and that is along the x-axis, and then 5 grid lines along the y-axis. And spacing, here we have the center to center spacing along the x-axis is first 5657 mm, 5470, and 5613. You can copy this. You can copy these dimensions onto a separate sheet of paper so that you don't have to come to this architectural plan time and again during modeling. And along these, another direction, we have center to center spacing is 3684, 4481, 6749 and 5151. So this is about the AutoCAD plans and elevations of our building. So let's start with the modeling of this building in ETABS. I have my ETABS open there. Go to new model. And use built-in settings with display units, metric SI, steel section database IS 800 or Indian steel design code IS 800, and concrete design code is still IS 456. We are only using the Nepal National Building Code for the earthquake load calculation and the calculation of other types of loads. Concrete design code is still, we still use the concrete design code as the Indian code, and then click on OK. So you can either go to custom grid spacing here itself, or you can modify the grids later on. I will just click OK here. The grids will be displayed on our screen. So I will choose to close this model explorer for now, and then we will modify the grids now. For that, right click, go to add modify grids. First, let's modify the grids in the horizontal direction. So here, go to modify show grid system, and we will display our grid data as ordinates here. Okay, let's not display as ordinates here. We will display the grid data as spacing. So let's see first. A, B, C, D here. This spacing first in this first row means this is the spacing between grid A and grid B. So we had that spacing is, let's look at our plan again. Grid A and grid B 5657. Since this is in meter, 5.657. Similarly, between B and C we have 5470. So 5.470. And finally, between C and D, our spacing is 5613. So 5.613. Now let's go to the Y grid data. We have 5 grid lines in the Y grid data. So add one grid line at the bottom. We have 1, 2, 3, 4 here. If we add, a 5th grid line will be added. So the spacing between 1 and 2 grid line, this means the grid line at the bottom side of this grid shown in the diagram. So don't get confused. This spacing 1 and 2 is, if you go to your AutoCAD plan, not this here, because our grid spacing starts with 1 from this end here, but in AutoCAD the grid 1 starts from here instead of 5. So first 1 and 2 grid spacing is this 5151. 5.151. Second is, you can similarly go to your AutoCAD and see the dimension there and use that dimension here. I have already copied that dimension. So the second one is 6.749. The third spacing is 4.481, and the fourth spacing is 3.684. And then go to the bottom and then click on OK. My OK is not being displayed here due to the screen resolution. There will be OK button at the bottom of this form. Click on that OK. So our horizontal grid system has been modified. Now let's go to our story data. Remember, we have how many floor levels? We have 8 floor levels excluding base. Let's see here. If this is our section, then this basement level minus 3600 is the base. Then we will have first floor level here or here. Okay, let's count the number of floor levels excluding this base. 1, 2, 3, 4. Okay, let's do again. Sorry. This is our base. 1, 2, 3, 4, 5, 6, 7, 8. We have 8 floor levels. So what we'll do is we have up to story 4 here. So we will click on this quick add story. Story 5, story 6, story 7, story 8. And after quickly adding these stories, then we will modify the story data by clicking here. So let's rename the story first. This is base okay. Now the story 1 will be, let's look here. Our story 1 will be this floor level here, the plinth level. So let's call it PL, plinth level. And then first floor, second floor, third floor, fourth floor, fifth floor, sixth floor, seventh floor, including the plinth level since we have 8 floors. Or you can rename this as first, second, third, fourth, fifth, sixth, seventh, eighth, or whatever you want to do. I'm just renaming these as plinth level. That means the slab level of the basement, and then first, second, third, fourth, fifth, sixth, seventh. So our story height is 3.6 for all stories. So I'll just copy this and then paste here. And elevation, it will be automatically updated based on our story height. And let's look at this master story concept. We saw that in our AutoCAD plan, the first floor level to our fifth floor plan were same. The arrangement of the architectural plan or the arrangement of the rooms inside these floor plans are the same. We have this big exam hall here, we have the control room, we have the waiting room, and then we have toilet and storeroom here. So the architectural plan is the same for first to fifth floor. So in this case, what we can do is we can assign any of this story from first to fifth floor as the master story, and then we can assign remaining other 4 stories as similar to the master story. So what I will do is this first floor level I will assign as master story and other no. I will assign one master story, this first floor level. First floor level means this first floor plan I am assigning as master story, and then I will do what I will do is this from second story I will write is similar to 1F. This 1F option is displayed here because we have assigned this first floor as the master story. So we can assign other stories as similar to the master story. So our remaining 4 stories from second to 6th are all similar to the first floor, and 7th floor is similar to none. So it's okay here. So the advantage of assigning master story and assigning other stories similar to the master story is that if we make any change to the master story, then automatically that change will be applied to other similar stories also. For that, we have to select the option of similar story. We will see how to do that, but that is the advantage of assigning master story to any of our floor levels. So click on OK. Click on OK. Okay, this is our grid lines here. So before proceeding any further, save the model. Go to File, Save, and save to your desired location with your desired name. Multistoried RCC office building. So now before proceeding with the modeling in ETABS, what I want to tell you is to go to our YouTube channel and search for our playlist on the seismic resistant design of RCC residential building. That is one of our first lecture video series. And if you go through the videos in that playlist, there are about 16 videos, I think. If you go through those videos in detail, you will be familiar with many concepts practically in ETABS and some theoretical concepts also. And if you follow our other playlist after watching that seismic resistant design series, then it might be very easy for you to go along with our other video lecture series. So I will request you earnestly to go to our YouTube channel and search for that playlist and watch all the videos of that playlist first. So let's proceed with ETABS now. Let's go to define. We will define material first, material properties. Some default materials are already defined here. We will add new material. Region India. Material type. First we will define rebar, and rebar we will define 500 grade rebar here. Click on OK. Now HSYD 500 is added on this list of materials. Now for concrete materials, what I want to do is add new material, concrete. I want to use YUM25 grade concrete in columns and YUM20 grade concrete in beams and slabs. This is our trial at first, and if the strength is not up to the required minimum, or if we have over designed, then we will change the grade during the process of design itself. But first we will define two grades of concrete here. First is YUM25 and another is YUM20. Okay, let's not do that. Let's only define YUM25, and we will use YUM25 grade concrete for all structural elements. Now after defining this, we can delete these other materials. Okay, you cannot delete this. So leave these materials as it is and then click on OK. Now after defining materials, we will go to define the frame and slab sections. So go to define section properties and frame section. Let's add new property. We will add a concrete rectangular column at first. So let us choose the size of our column as 500 mm by 500 mm at first. So I will name this as column 500. Material will be YUM25 and our section dimensions will be 500 and 500. Let's go to reinforcement, modify show rebar. This is our column design. Our rebar material will be HSYD 500. Our reinforcement configuration will be rectangular. The reinforcement is to be designed. Clear cover for confinement bars 40 mm, and for now let's keep these number of longitudinal bars along 3 direction face and 2 direction faces, both 5 and 5. Other, we will leave those values as it is and then click on OK. And for these property modifiers, if you remember our last lecture, we discussed the property modifiers or stiffness modifiers also. NBC 105 in its clause 3.4 gives us the effective stiffness of different components. And you can see here that for columns, the gross moment of inertia will be taken as, or the effective moment of inertia will be taken as 70% of gross moment of inertia for flexure and 40% for shear. So what we will do here is that first we will left click on this modify show modifiers, and then I will use the stiffness modifiers is for shear area in 2 direction is 0.40, shear area in 3 direction 0.40, moment of inertia about 2 axis 0.70, and moment of inertia about 3 axis 0.70. OK, and then click on OK. Our column is defined. Now we can delete other properties here. So I'll go to delete multiple properties, and I will delete all other frame sections except the one that we just defined, that is column 500 by 500. Okay. Now let's go to defining beam. Click on add new property, concrete rectangular beam. Let's rename our beam as BEA. Let's suppose that the size of our beam is, let's suppose it is 12 inches by 15 inches for now. That means 300 divided by 350. 15 inches means, okay, let's suppose 300 by 400 size beam. This is a trial and error approach. You can either perform the preliminary design that we learned in our previous lecture series, the one that I discussed just a moment ago, or you can use these trial values. So if you are used to designing structure in ETABS, then you can guess such a trial value which will be very close to the design value that will come later after the design, or you can perform some preliminary calculation. For now, I will be using the size of beam is 300 by 400. The material will be M25. The depth will be 400 and the width will be 300. Left click on this modify show rebar for reinforcement. Ours is a beam design, so M3 design only. Rebar material HSYD 500. And let's see that what is given here. Cover to longitudinal rebar group centroid. So what we will do is, let us suppose for top bars, let us suppose our clear cover is 20 mm plus the diameter of our longitudinal bar, or first the diameter of our steed up is 8 mm, 8 plus, if we suppose the diameter of our longitudinal bar is 20 mm, then 20 divided by 2, it will come out to be 38. So let's put the cover as 40 mm and 40 mm and then click on OK. Now again left click on modify or show modifiers. Let's see here again. For beams we have shear stiffness 40% and flexural stiffness 35%. So for shear area in 2 and 3 direction 0.40 and 0.40, and moment of inertia about 2 axis and 3 axis 0.35 and then 0.35. Click on OK, click on OK. Now we have defined 2 frame sections, 1 beam and 1 column, and then click on OK. Save your model. Now let's go to defining slab sections and wall sections. Wall sections, because we have shear walls and basement walls in our building. If you go to our AutoCAD plan and go to our basement floor plan, we will have basement walls in all the sides except the side for this vehicular entry. There will be no shear wall between this grid B and C here, because vehicles will have to enter into the basement from this side. Otherwise, there will be basement walls on all other sides. And then we have lift shaft here. And let us suppose this lift shaft is made up of RCC concrete wall. So for that, let's go to define section properties and slab section. First, we will define 2 slab. You can either define a slab or modify the properties for these 2 slab property, plank 1 and slab 1. So let's go to plank 1, modify show property. I will rename this as slab 125. The slab material will be M25. The modeling type will be cell thin, since this is our floor slabs. And then the type will be slab here and thickness will be 125 mm. And then click on OK. Now I will modify this slab 1 here, modify show property. I will rename this as stair slab, since this is the slab that I will be using to model staircase. The slab material M25, modeling type cell thin, and thickness I will use the same thickness 125. Click on OK. Now our slab sections have also been defined. Remember, I am going a bit fast in this series because I am expecting that those who are watching this series will be used to with basic modeling features, basis analysis and design features in ETABS. The assumption is that those who are watching this series are already acquainted with the basic procedures of modeling, analysis and design in ETABS. So let's continue. I will go to define again section properties and wall sections. In wall section, let me modify this wall 1 property here. I will specify this as first basement wall. Basement wall. property will be same, specified one here. Wall material will be M25, modeling type cell thin, and thickness, let us suppose we have 8-inch thickness basement wall, so thickness will be 200 mm, and then click on OK. Now I will add another property for shear wall. I will rename that as shear wall, and other features will be the same as that for basement wall. M25, cell thin and 200 mm thickness, and then click on OK. We have defined the wall also, and then click on OK. So in this lecture, up till now, we have made the grids in both horizontal and vertical directions, and then we have defined materials and some section properties. Now after that, we can, okay, let me just save the model. In today's lecture, what we will do is we will complete everything related with the definition part, this define tab in ETABS. We have defined up till now section properties. We will define diaphragms, and we will define mass source, load patterns, load cases, load combinations, and then model the structure. And in our next lecture, we will apply the loads and then perform analysis of our building in ETABS. So let's continue. Okay, let's continue with our defining options. Let's go to define and diaphragms. We have 8 floor levels here, so we have to define 8 different diaphragms, and all diaphragms will be rigid diaphragms. Rigid diaphragm means which has infinite in-plane stiffness. It does not bend in its own plane, but rather it has infinite stiffness in its own plane. So add new diaphragm, D2 rigid, add, okay, D3, D4, D5, D6, D7, D8. We have 8 diaphragms defined here now, and then click on OK. Go to save the model, go to define option again, and under define, before defining mass source, we have to define the load patterns. So we may have to define some functions relating to response spectrum also, but we will see that in the second part of this series. First, we will perform the equivalent static design or analysis, and then we will go to response spectrum. So for now, we will not be dealing with the definition of response spectrum function and response spectrum load cases. We will go to load patterns first. Okay, we have dead and live loads already here. So another type of load that we discussed during our first lecture was the storage live load. So for this live load, let's rename this as live capital N, which means the normal live load, and then we will modify load, and then we will define another load here, live loads. Live sto means storage live load, and then add new load. Similarly, we will have live loads on our stair, so we will define live stair. Again, this is the live load, and then we have a roof live load. We will define as roof live, and then add new load. Now besides this live load, we will have other dead loads also. For example, we will have floor finish, which is our super dead, that means superimposed dead load, or you can select this dead load also and self-weight multiplier 0. Add new load. Another dead load that we may have will be the masonry wall load. So masonry wall load, type will be dead, self-weight multiplier 0, add new load. Similarly, another will be the partition load, type will be dead, add new load. And if we have water tank in our building, then we can define water tank load also. And water tank load you can either define as dead or live. For now, I will be defining it as dead load, add new load. And finally, since we have swell pressure, we will also define swell pressure here. And we will define swell pressure as dead load. You can define as dead or live, but for now I will define swell pressure as dead load and then add new load. Okay, we have defined all the dead loads and live loads here. Now we will have to define some earthquake loads. And remember what we discussed in our previous lecture. we discussed that the performance characteristics have to be analyzed according to our NBC 105 2020. And in analyzing the performance characteristics or in verifying the performance requirement, we have to check for both ultimate limit state and serviceability limit state. For that, what we will do is we will define two different kinds of earthquake loads. First will be the earthquake load for ultimate limit state. So in that, EQX in X direction, earthquake load in X direction, ultimate load, our type will be seismic, and our autolateral load will be user coefficient. Since the Nepal National Building Code is not included in ETABS, we will provide coefficients by ourselves. So select user coefficient and add new load. Similarly, EQY for ultimate limit state, other options same, add new load, and EQX for serviceability limit state, SLS, add new load, and EQY for serviceability limit state, EQY SLS, add new load. So if you click on any of these four earthquake loads and then click on modify lateral load, you have different options here. The direction and eccentricity ratio, the factors. These are the main factors that you have to enter because these are our user coefficients and our story range, on which story our earthquake load will act. We will see how to calculate these factors and other things here in our next lecture. And we will modify these factors and story range there. For all these four different types of earthquake load. For now, just leave them as it is. Click on OK. So these are our load patterns or loads that may come onto our structure. If we have missed any load, then we can define or add that new load pattern in our later stages also. For now, I'm defining these different types of loads and then I will click on OK. And then save. So we have defined the load patterns. Now for these load patterns, load cases will be automatically defined. You can see here. Okay. And then we will define our load combinations. Before defining load combinations, what we will do is we will define the mass source. And in defining mass source, you saw in our previous lecture, you learned that the mass source should be composed of, mass source means that mass that is contributing to the seismic weight of our building. And seismic weight will be determined as given in table 5.1 of NBC 105, which says for live load storage category, you have to use a factor of 0.60, and for other purpose live load, you have to use 0.3. You have to use the full dead loads, that is factor 1 for dead loads, and for roof live load, you don't have to use any factor because we suppose that the roof live load will not act in the composition of seismic weight. So for this, you can either delete this mass source and add new mass source or just modify this and set it as default. Since there is only one mass source here, it is already set as the default mass source. Let's go to modify show mass source. Let's uncheck this element self mass because we will be adding the dead load of our elements in our table on this right hand side, and then check this box specified load pattern. So for all dead load, use multiplier 1. So for dead load 1 and floor finish 1, masonry wall 1, partition 1, water tank 1, and swell pressure 1. So if you had assigned this water tank and swell pressure as live load, then you would only have to use 30% of this. But since we are using these as dead loads, then the multiplier will be 1. The swell pressure you can also ignore during this calculation of seismic weight. But for now, we have selected this and assigned the multiplier 1. And finally, live load normal, you will use factor 0.30. Live load storage, you will use factor 0.60. Live load stair is also a normal live load, so factor 0.30. And this roof live load, you do not have to include in seismic weight. So let's leave this roof live load. So these are our loads composing, or which determines the composition of our seismic weight. Click on OK, click on OK. So you have defined the mass source also. Let's save the model. And now finally, let's go to defining the load combinations. So let's go to define and load combinations. If it was your any code that is already incorporated in ETABS, then you could as the default design combos. But since this NBC code is not included in ETABS, you have to define manually. For that, first let's go to our previous lecture and see what we learned in defining the load combinations. Okay, this was our slide on load combinations. We saw that ours is a structure with parallel system. That means our lateral load resisting elements are oriented along mutually orthogonal horizontal directions. So we will look at clause 3.6.1 of our NBC 105 code. So there are two different types of load combinations here. First is the 1.2 dead load plus 1.5 live load. So for this, what I will do is, this 1.2 dead load and 1.5 live load means this dead load includes all the different types of dead load. That means our floor finish, masonry, partition, soil pressure, water tank, all these different types of dead load are included here. And in this live load, all different types of live load are included here. So what let's do, before defining this 1.2 dead load plus 1.5 live load, let us combine all the dead loads into one combination first. For that, add new combo, rename this combo as one dead load and include all the dead loads that are here. The combination type will be linear addition. So include all the dead load here. For example, dead load with a scale factor 1, and then floor finish scale factor 1, masonry wall 1, partition 1, water tank 1, and then soil pressure 1. So all the dead loads have been included in this separate load combination 1.0 dead load. Okay. Similarly, add all the live loads. For example, add new load. Okay, you may not have to do a separate combination for live load, but for example, I will do here 1.0 live load. Add all live loads here, whether it is normal live or storage live or our stair live or our roof live. Add all live load here and then click on OK. Now finally go to defining load combinations according to our code. First is 1.2 dead load plus 1.5 live load. So add new combo 1.2 dead load plus 1.5 live load. Now instead of adding all the dead loads here and assigning them scale factor 1.2, what we can just do is we can select the 1.0 dead load combination here. This includes all the dead load and then assign the scale factor 1.2. So this makes our job easier. And then again, instead of adding all the live load, what I will do is add this combination 1.0 live load and add the scale factor 1.5 here, and then click on OK. Our load combination is defined. Now it is a little different for another load combination here. It says dead load plus lambda times live load plus earthquake load, or plus minus earthquake load. So this value of lambda will be 0.6 if it is a storage live load and 0.3 if it is normal live load. So what we will do is we will add new combo and dead load plus lambda times, okay, let's write is L times for lambda times live load plus, first we will include EQX ULS. So what we will do is we will include this 1 times dead load and scale factor 1, and then we will not use this 1.0 live load here because the scale factor will be different for different type of live load. So we will select this normal live load live and then assign scale factor 0.3, and then we will select again live storage and assign factor 0.6, and stair live also is normal live load, so 0.3, and roof live 0.3 again, and then click on OK. Now next node combination will be minus EQX ULS. So instead of defining a whole new combo, select this load combination and add copy of combo. Change this name to minus EQX ULS. So okay, we have made a mistake here. We haven't added EQX load here. So click on this load and go to modify show combo and add another new load here, EQX ULS, and then use the scale factor of 1 and then click on OK. Now select this load combination and then add copy of combo. This will be minus EQX ULS. Change the scale factor of earthquake load to -1. OK. Again add copy of combo. This will be now plus EQY ULS. Change this EQX to EQY ULS. Click on OK. And select this Y combination and then click on add copy of combo, and this will be now minus EQY ULS. Change this scale factor to -1 for EQY and then click on OK. So if you ignore this 1.0 dead load and 1.0 live load, we have 5 load combinations here. In our codal provisions also, according to this code, we will have these 5 load combinations are sufficient. What I would like to do is, I would like to add a new combo. Name will be 1.5 dead load plus 1.5 live load. I will select the load combination 1.0 dead load with scale factor 1.5 and 1.0 live load with scale factor 1.5, and then click on OK. I will be using this load combination to design the basement or to design the foundation of our building. Then our load combination defining will be complete. So let's click on OK and then save the model. So we have completed the defining portion, and after defining everything that we need, now let's go to modeling our structure. You can see here that in our AutoCAD plan we have columns in these grids: A, B, A1, B1, then A2, B2, C2, D2, A3, B3, C3, D3, A4, B4, C4, D4, and then A5, B5, C5. We don't have column here in these two places and here. So let's go to quick draw columns option from draw, or you can select this shortcut option here also. Quick draw column. Select the property as column 500 over 500. At the right and bottom, select all stories, and then select the grids on which the columns have to be drawn by doing like this. This is an easy way to draw columns. And then click on escape or click on this select mode again. Now if you go to our top floor, you see that our columns at this 1, 2, sorry, not this here, 1, 2, 3, 4 positions will end in the 5th floor itself, and there will be balcony here. So what I will do is I will go to our top floor using this arrow, move down in the list, move down in the list. Okay, since it is lagging a bit in my ETABS, what I will do is I'll go to option, graphics mode, and standard graphics. It's okay now. Save the model. I'll go to my top floor, which is 28.8 meter, and I will delete this. How many columns should I delete? Let's look here again. 1, 2, 3, 4. Since there will be no rooms above this floor, I will have to delete these 4 columns. So I will select these 4 columns here. Now let's look here. All the columns are being selected because what we did was we have selected all stories here. So let's change this to one story. Go to our topmost floor, which is 28.8 meter. Select these 4 columns and then delete these 4 columns. Click on delete. Now these columns have been deleted. Now after drawing columns, let's draw beams. To draw beams, I am again going to our plinth level slab, which is at a height of z equals to 3.6. Now our beams will be at every location connecting these 2 columns. So what I will do is I will select the option all stories again and then go to this quick beam draw option and then select our beam 300 by 400. Now I can either draw beams in this way or I can click on this individual grid which will take comparatively more time. So this is our beam. Now let's go to our top story again. There won't be beams here. So let's select this one story option. Let's select the beams which are not necessary and then click on delete. Okay, this is deleted. Now we will draw slab. To draw slab, what we will do is okay, we will draw slab in our a little bit later. Before drawing slab, let's draw the basement walls. So to draw the basement walls, select this one story option. Go to our plinth level, which is at 3.6 meter height. And you know that when you are drawing columns or walls in ETABS, if you draw on the first floor, then that wall will be drawn at below that first floor. Nothing will be drawn above the floor on which you are drawing, but that wall will be drawn below the floor on which you are drawing. So let's go to our plinth level. We saw that our basement wall is present in every corner except this, between grids B and C in 4B and 4C, from where the vehicles will make entry into the basement. So what I will do is I will select this quick draw walls option and then choose the property as basement wall, and now I can draw basement walls here. You can see in the 3D diagram side by side that our basement walls are being drawn. There won't be basement wall here for entry into the basement, and final basement wall will be present here. Select this option and then save the model. Now we have to draw the lift core. Okay, let's see here. Where is our lift core? Our lift core or our lift shaft is present here between this 2 grid and 3 grid. And this lift shaft has a distance of 1.55 in this direction and 1.65 in another direction. So since this lift shaft is at a distance of 1.65 from this column, what I will do is since our lift shaft is present between these grids 3 and 4, for now let me select this wall here and then delete the wall here, this wall here, because okay, let's delete the wall here. Now select all story option here. Okay, for now let's select only one story, and then we will first draw a joint object. We will draw a joint object here in this corner and in this corner to draw our lift core. So let's go to draw joint object. Our joint object will be in the positive x direction 1.65 meter, which is 1650 from this point here, and another point will be at a distance of 1550 in y direction, 1550. Again another point will be at a distance of again 1650 from this point. So we will draw our lift shaft in between these joints. Now go to all stories and then draw lift core. Use this draw walls option. Select the property as shear wall and then start drawing here. From here to here, from here to here, and from here to here. So this will be our lift core. And then you can draw the basement wall in this remaining portion. Select one story option. For this blank, select this draw walls option and then select the property as basement wall, and then draw basement wall from here to here. If I had drawn this lift core on this whole basement wall, then in this area there would be overlapping of our two basement wall and shear wall. So I deleted this basement wall first, drew the lift shaft, and then drew the basement wall in the remaining portion again. So now let's go to our 3D diagram here. You can see that our lift shaft or the shear wall for our lift core ended here. But many a times what happens is that you need more space above this topmost floor known as headroom for fixing these different mechanical equipments of lift wall. So you may have to now construct these lift walls above these floors also for a certain height. Let us say that that height is 1.2 meter for now. So what we will do is from this point here up to a height of 1.2 meter, we will draw these shear walls. For that, what we will do is we will go to first right click on this model, go to add or modify grids, go to modify show grid systems, and then click on this reference plane here. We will add a reference plane at a ordinate of our height of our building is 28.8 meter, so 28.8 plus 1.2, so 30 meter, and then click on OK. Click on OK. You can see this reference plane is added now. Now go to this reference plane in our plan view, G1 reference plane at 30 meter. So this is our reference plane. Draw a joint object similarly to what we did before. Draw joint objects. First at a distance of 1650 from here, and then 1550 again from this point, and again 1650 from this point. Close this, go to draw wall option, select the property shear wall, and now draw the shear wall from here to here. Okay, what is happening here? Let's see. We have selected this one story option. Now shear wall is being drawn in all these floors. So what I will do is, for now I will select these from wall sections. I will select all of our shear wall, and then I will delete these shear walls and I will draw them again. And go to draw option, shear wall is selected. From from this joint to here, from here to here, and then from here to here. Okay, our drawing of our shear wall is completed. So up to now, what we did was we modeled all of our elements, including the beam, the columns, and then the basement wall and shear walls. Now we are left with modeling of our floor slabs and then our staircase. We will look at the modeling of our staircase in our next lecture. For now, we will look at the modeling of floor slabs only. So what I would like to do is, let's select this all stories here, and then let's go to this quick draw floral wall option, and then select the property of slab 125. So here will be our slab, here, 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 similarly here won't be slab since we have a staircase here. And for this section, let's select this draw floor wall option and then select the joints. Since there won't be slab in this lift core, we can't use the quick draw option. So this is our slab. Now let's go to our top floor. Okay, our slab is being drawn at the bottom also. We don't need that, so click this one story, select these slabs and delete them. Go to the top story. There won't be slab here. You can close this lift core also, so go to this quick draw option, select slab here, and then draw slab here also. This will be the end of our staircase cover. So this completes our modeling here of our floor slabs. Save the model. If you want to see the extruded view, select this. This will be the extruded view. Again, select this for going out of extruded view. So in our next lecture, we will see the modeling of staircase and then application of load. This brings us to the end of our today's lecture. We'll see you again soon. Thank you.